Hello, everyone. This is Chao from Snarkify. Today, I'll talk about a Sirius, a generic open-source circuit fogging framework. My talk consists of 3 parts. The first part, I will give a brief introduction as a background, and also the overall architecture of our project. The second part, I will talk about the detail, like how do we implement the folding scheme. And the last part will be what's next. So this is a problem we are trying to solve. Suppose f is a function. It takes 2 inputs. One is a state variable, z-in, and one is an auxiliary variable, w, and the output is z-out. So we will assuming the z-in and z-out has the same dimension, so we can recursively apply the same function again and again. So with this setup, this is a typical situation for the IVC, which stands for the incremental verifiable computation. And there are various applications for this kind of setup. For example, in the ZKVM domain, you can assume the Z is just the state of the register, and F will be just a microprocessor. And in the domain of the ZK rollup, you can assume the Z in and Z out is just a blockchain state, and the F is just apply a bunch of transactions to modify the state. So you can see it's widely used in different scenarios. And here, I list 3 different approaches to solve this problem. The first one, we call it naive approach. So basically, you have to fix the step size. For example, n equals 10, and you write all of the 10-step circuit into a giant circuit and feed all of the input as a witness and try to prove it. With this approach, basically, you lose flexibility and has a lot of drawbacks. For example, whenever you want to change the step size, you basically have to rewrite the whole circuit. And also, the number of size will limit the size of a circuit and the memory usage. So no one will use this approach. So the second approach, what I call it proof-based IVC, which is basically for each of the computation, when you write a circuit, it consists of 2 parts. The first component of a circuit is basically a step circuit to execute the step function, basically the f. So basically, given zi, the circuit will output zi plus 1 correctly. A second component will be just the verifier circuit to verify the previous proof. So basically, for each step, you verify the previous step. So basically, you get a proof or proof or proof, and so on. At the last stage, you verify it once and prove all of the previous steps. So this is a proof-based IVC. And the third one is the folding-based IVC, the first proposed in the NOVA paper. So this approach, the difference between the proof-based and the folding-based IVC is that we don't have to create a proof at each step. Instead, we just capture the essence of the information from the previous circuit and fold it into a running accumulator. So basically, whenever you folded the previous circuit's information into a running accumulator, the accumulator consists of all the information from previous steps. So with this setup, as you can see, at each step, you don't have to create everything. You don't have to create the proof. You just have to fill all of the witness, calculate the witness, as well as the commitment to get the instance. So this is less overhead for each step. And this is what we are going to use. And this picture is a basic project architecture in Sirius. So basically, there are 3 layers: the front layer, middle layer, and the backend layer. So the front layer, assuming a user using the Halo 2 library, and he write a plunkage circuit, and we can convert his user's defined circuit into some intermediate representation, the IR. So in our case, there are 2 approaches. I think in the previous 2 talks, you already see them. So the first one is the SPS, called the Spatial Soundness Protocol, defined in the Protostar paper. The second one is the CCS, the customizable constraint system, defined in the CCS paper. So both of this approach can capture all of the widely used constraint system up to date, like the Planck, R1CS, and AIR. So we are using the SPS approach defined in the Protostar in our project. Later, we might add the implementation for the CCS. So in the middle layer, after the front layer convert a user-defined circuit and information into the intermediate representation, IR, we can fold the user's n steps of computation one by one. So this is what we apply the folding scheme in the middle layer. At the end, we'll write a ZK snark for the decider, so decide all of the n steps computation is correct or not. So this is basically the overall architecture. So currently, the blue box is indicate our current progress. So we are in the middle of the folding scheme, and we almost finished the lookup argument as well as the IVC circuit implementation. After that, we'll add the backend later. So the second part, we'll talk about the implementation for the folding scheme. And here, this table definition, there are two columns, the straight column and the relaxed column. So the straight column, what I mean, is basically a Planck's relation. So assuming, for example, we are using the Halo 2 library as a front end. So basically, the P is a polynomial relation, and in the Halo 2's terminology, it's basically a custom gate. And you can assume each the Fi is a fixed column or selectors, and the Xi is the advice column or instance column. So with this setup, this custom gate is defined over all of the column variables, and has to be satisfied row by row. So if you're familiar with the Halo 2 library, you can imagine you have a big table and multiple columns, and the custom gate is defined over these columns, and it has to be satisfied one by one. So here, this is what I call the strict relation. It's just a custom gate satisfied by the Planck's relation. And the witness, just the concatenation of all the advice columns. And the instance here is basically the commitment of witness, and also the X0 here is actually, we capture all of the previous IVC circuit information using a hash. So here the PP is kind of public parameter, I is the current step, and Z0 is the initial input, and the ZI is the output after I step, and the capital UI is actually, I defined in the second column, the relax. So basically what I mean relax is following the Nova's paper definition, but from the IVC terminology, it's just a accumulator. And you can, when we do the folding, you actually don't touch the fixed column because the circuit structure is the same. So when you fold two circuits, the fixed column is the same, but the advice column, we will do the random linear combination to combine it. However, if you random linear combine these advice columns and the instance columns, you can check the polynomial relation or the custom gate over each row is no longer 0, but some non-zero value. So we just call it arrow vector here. So basically, after you fold into instance, you get a polynomial relation equals some arrow vector. So we have to put this arrow vector as a witness for the relaxed witness. So basically, for the relaxed witness, it has the previous witness for each column, and also the witness for the arrow vector. And of course, the instance will be just a commitment of it. And here, you can see the lambda is just some factor, the slack vector, to make the polynomial relation homogeneous. And we will see in the next slides why we need the polynomial relation to be homogeneous. So this is all the setup or definition will be used later. So these slides explain how the folding works. So this is a prover part of the folding. So assuming you have two such relations, P over W1 and W2. So the W1 and W2, you can imagine just multiple columns. And they share the same structure, Fi. So I didn't write it here for simplicity. And also, I didn't write the slack variable lambda, which is make the polynomial homogeneous. So now, assuming the polynomial is homogeneous with degree D, so you can directly calculate with this multilinear combination with W1 and times R times W2. R is just some random number. This vector random combined together, if you evaluate this polynomial relation, it actually satisfies this complicated relation. So basically, the E1 is the error vector from the first instance or first witness, and the E2 is the error vector from second one. And when you do the folding, you actually get a bunch of cross terms. So basically, each TI is a vector. And as you can see, you can calculate the folded error vector in terms of previous two, together with some cross terms. And luckily, When we do the folding, you actually folding a running accumulator with the previous strict Planck gate relation. So that means one of them is always 0. So here, E2 is always 0 when we do the folding. So 0 times ln R times D is just 0. So you don't have to do anything for that term. So with this setup, this is the prover side. But for the IVC verifier part, we have to verify this calculation is correct. So basically, we use a homomorphic commitment scheme to commit these vector relations. So basically, from the left-hand side, the E after commitment it should be equal to E1 plus RD times commitment E2. Here is just a vanish. So you have a D minus 1 terms of commitment of the cost terms. So this is where we get D minus 1 group scalar multiplication for the cost term when you calculate the folded of the arrow terms. And the one here is actually from the commitment of witness. When you do folding of witness, you have to calculate a scalar multiplication again. So basically, if you have a degree D polynomial, when you do this folding, you actually have to calculate the D group scalar multiplication in the verifier. So because in the verifier, we have to verify every logic in terms of a circuit, and this is a dominate operation. So roughly, for each group scalar multiplication, you have around 10,000 rows of constraint. So we want to minimize the number of constraints. That's the reason I think Paris mentioned the blow up of degree. If you have a high degree, then the number of group scalar multiplication is large. So basically, you have D times group scalar multiplication of the rows. That's a lot. And luckily, using the protostats optimization, we can reduce the high degree into only 3. So in this case, no matter how high the degree it is, we can always use at most 3 scalar multiplication in our IVC circuit. So the next, I will talk about how we do the copy constraint in Sirius. So basically, if you're familiar with the Planck proof system, the copy constraint basically assuming you have some circuit defined, some input wire of some circuit is equal to some output wire of the circuit. So you have to make sure these 2 wires value equal the same. So this is what we call the copy constraint. So basically, when the user writes a circuit and he defines the copy constraint, he actually defined you can convert this as a permutation between all the wires. So suppose there are totally n wires with a copy constraint defined, you can find the corresponding permutation over these n wires. And essentially, this is the relation, the W sigma I equal Wi has to be satisfied. Equivalent to the copy constraint has to be satisfied. And again, you can convert this as a permutation matrix. So basically, a permutation matrix times the witness, the concatenation witness should be equal itself. Here I give a simple example. We only have 3 wires, and the user defines the first wire equal the second wire. So it means 2 and 1 should be equal. And after you convert this into a permutation matrix, it looks like this way. So a 3 by 3 matrix, P times W1, W2 times W3 equal itself. So as you can see, this is a linear relation. When you do folding, it's basically, this is unchanged. You get it for free with this setup. So the next part, or the third part, is a lookup support we use in Sirius. So actually, in the line, I already explained a lookup support, like a lookup argument using log derivative. But here, I will just briefly overview it in terms of the Halo 2's terminology. So in Halo 2, he defines 2 expressions, lookup expression and table expressions. So lookup expression is defined over advice columns, the xi, and the table expressions defined over the fixed columns, fi. So actually, there is some dynamic lookup can define on the advice column. But in this case, the trait or the folding of this lookup argument will be slightly different. So here we only explain the lookup table expression is just over the fixed columns. So it means given this lookup and the table expression, you can evaluate row by row to get the lookup vector Li and the table vector Ti. And the lookup argument is trying to prove the set of Li is belong to a subset of Ti. And as you're already familiar, we can use a lookup derivative to convert this problem into this edge-back relation. And I think Lion already explained the intuition. Here, I just explain my intuition. So assuming one of the LIs not belong to the right set, so it means the left-hand side has a pole at a negative LI, but the right-hand side don't have a pole. So this equation can never satisfy it. So this is just a simple intuition. So this is the PROGCRYPTO protocol over the log derivative, because we already have converted our lookup relation into this log derivative algebraic relation. So we can design a protocol. This is a 3-round spatial soundness protocol, and we can fold it. So in the first round, the prover will send 3 or concatenation of these 3 vectors, W, L, and M to the verifier. So M is just a multiplicity vector. And the verifier will respond with a random value R. After the prover receives the random value, the prover can calculate the H and G vector. So as you can see, the H and G vector is just the left-hand side and the right-hand side of the log derivative formula. So the prover will send back the concatenation of H and G vector. The verifier will just check these 4 relations. So as you can see, the first relation is to make sure the lookup expression is actually equal little L. And the last 3 is just to check the algebraic equation from the log derivative lemma satisfied. So you can imagine this is actually just a bunch of custom gates. It's just some polynomial relation. We can use the same trick as we have for any arbitrary custom gate to fold this relation. So it's quite general. And we already know how to fold the alien custom gate. So basically, we can know how to fold this kind of relation. So this is how we deal with the lookup argument. So the next, we'll talk about the design of the IVC circuit. So basically, this is follow the Novas paper as well as the Novas implementation. So at each step of the folding verifier, so we basically have two major components. You have the step circuit to ensure the correct execution of the function f. So basically, given the zi as the input at step I, after this circuit, it will ensure the output is zi plus 1 correctly. So this is one of the first piece of the major component. And the second component is you have to basically instance to fold it. So the little UI is coming from the previous step of this big guy. So because you apply this circuit again and again. So little UI is from previous step. You get the strict instance I defined in the table, if you still remember. And the capital UI is actually the running accumulator, or the relaxed instance. So basically, at this second component, you will fold from the previous steps UI to the capital UI to get an updated accumulator. And as you can imagine, we can prove after the accumulation, the capital UI plus 1 capture all of the information from previous steps. So this is 2 of the major components of the IVC circuit. And of course, we have to do some bookkeeping, like verify the input of this, like capital UI ZI is actually from the previous steps. So this is just a bookkeeping to make sure everything is sound. So this is for a slide for any developer who is interested to integrate with our Sirius library. So for example, currently we support the Halo 2. So if you are a Halo 2 developer, you can, and your calculations can fit into this category, basically repeated computation. This is how you can integrate with our library. So if you're familiar with the Halo 2 circuit development, this is almost the same as the Halo 2 circuit trait. So basically, the first one, you have a configuration for your circuit. This is exactly the same as you did for your circuit. So your own circuit, you don't have to change it. The second one, synthesize step, is very similar to the synthesize trait in the Halo 2. So basically, this is execute the step function f from zi to zi plus 1. So this one, you have to slightly modify your existing synthesize method. So basically, you have to change the z in and z out to become a signed cell instead of just the value. And of course, z in and z out has to be the same dimension to fit into this whole category. So with this, if you implement this trait, our IVC circuit or the from Sirius can grab your your circuit into part of our big IVC circuit and fold it n times. And finally, we decided at the last step. So this is how we integrate the user-defined circuit. So the last one part is what's next. So here, let me introduce the tech stack for Snackify. So basically, we are ZKP acceleration platform. Our tech stack consists of 3 layers. The bottom layer is the Snackify cloud. Basically, it's a serverless cloud. You can easily scale up your GPU or Prover server and scale it down automatically when you don't use it. So basically, it's serverless. And it's already launched. Please check it out with cloud.snackify.io. And the middle layer is the GPU acceleration for the Prover. Basically, we call it cuSNARK. This is to add it into the backend of the cloud server. So when you prove something, you can use the GPU accelerations. And the top layer is what we just described, the Sirius. So basically, if you have some computation work repeatedly, you can use in this Sirius to fold your computation to speed up your proof generation. So together, this together is basically, we want to make sure it's kind of one click for the user to deploy his backend server and prove its circuit with minimal modification, of course. So this slide is a benchmark for the cuSNARK library. So currently, we have implemented the MSM acceleration, and this benchmark is from our cuSNARK versus the SSpark developed by the Supernational. And here, I think it's missing some bottom level hardware. We tested on the hardware A40 with 40 gigabyte VRAM and just one A40 card. And as you can see, this is the x-axis is a number of points for the MSM. And when the number of points go to 2 to 25, as you can see, there are about 38% performance gain for our library. So this is current our benchmark. We will continue to improve it. Yeah. So this is the roadmap. So basically, as you can see, we are still in the middle. And what's remaining? We plan to, in the next year, Q1, we plan to finish the lookup argument and IVC circuit, as well as the protostar optimization. So with this, all of this finish, the users, developers can just use in the libraries to give it a try. So you can just fold the library in steps with the missing thing, the decider part is missing. So we'll try to add it in the Q2. Basically, add a backend, IOP, and PCS. We plan to use the soundcheck protocol with some maybe most fastest polynomial commitment scheme. And we also plan to using the cycle fault to make sure the IVC circuit has only, before I didn't explain, the IVC circuit is actually, you have to have that cycles because of the multi-scalar multiplications. It happens in 2 fields. So we have to using cycle to speed up. And with the cycle fault, it should be faster. Yeah, so this is Q2, we plan to do this. And then last, if a blockchain developer, you probably want to verify your circuit after n-step on-chain. So we have to add this support for on-chain support. And also we want to add the R1CS or AIR to support other kind of library, for example, like a Bellman. So this is basically the roughly roadmap. And this is we open source now. This is the GitHub, and feel free to check it out. And also, you're welcome to contribute. If you want to submit any PR, you're always welcome. And also, this is a Telegram channel. You can also find it from the GitHub channel. So if you have any technical question, you can just post it, discuss it in this channel. So that is all my talk. And this is on reference. Thank you very much.
Thank you, Chao, so much for bringing these amazing libraries. I'm really looking forward to using that. So we have a few minutes for the Q&A. We have plenty of minutes. Yep.
Hi. Yeah, I'm really dumb, so you'll have to be a bit slow. But if you call back a little bit with the variable, go back to the identity matrix. I think it was sort of an identity matrix, not quite, but almost.
This one?
Yeah, I think there's a typo here. The right-hand side should be V2, V1, V3, right?
You mean the right-hand side, right?
Yeah.
W1, W2, W3, right?
It says 1, 2, 3, and you renumber it to 1, 2, 3? If I do the multiplication. Okay, so this one says that W1 is equal to what, W2?
Yeah, so this W is just the index for the witness.
Okay, so this just says that W1 is equal to W2 and W2 is W1.
Right. So if you times the first row with this, you get W2 equal to W1, right? If you check the matrix multiplication for the first row, and if you check second row times this, you get W1 equal to W2. And the third row, W3 equal to W3. So this is equivalent to that relation. So basically, it defines the wire equivalence, the same values, yes.
Why can't you just do variable renumbering? So it's a wire, you could just use the wire from the previous step as a...
No, so this wire is already folded together with the custom gate. So what I mean is you don't have to do any folded relation for this. So actually there are some conversion to convert the copy constraint into some polynomials. So with that conversion, you have to fold the polynomials. So with this setup, you don't have to fold it anything. Basically, it's linear. But you have to, the only thing is this is a sparse matrix. So we have to use some sparse matrix polynomial combination thing like a sparse to treat it separately. Yeah. Yeah.
Okay, so background is I'm also developing.
Up or down?
I'm also developing protester library. So my question is, considering you are using Halo 2 as a front end, my question is, do you have like a commitment to each column, or do you somehow merge them? So like for me, it's hard to see why, except of like copy pasting circuits, you have what is the advantage of using Halo 2 as front end?
Could you repeat? I didn't hear clearly.
Okay, in protester we can use both high degree gates and free linear combinations. When you are saying let's use Halo 2 as front end, you are removing from yourself the ability to use free linear combinations. So I'm wondering what's like, why are you considering to incorporate this trade-off back, so like unlock this ability at some point?
You mean why do we use Halo 2? Or no, yes.
Yeah, so I think that you're not using Halo 2 circuit for the front end, right?
Yeah. So we are going to support the, because for a Plunkish, we're just using Halo 2 for now because it's one of the most widely used for Plunkish proof system. And when we support, let's say, R16, we will import the circuit from the Billman library, for example. I hope, maybe we can discuss, yeah.